Okay, so before I start today, I just want to maybe talk to you a little bit about your AS results. So depending on what you have for your AS, okay, the full mark is 130. So if you don't know this, you should probably go and find out either from your exams department or your subject lecturers what your scores are for paper one, the objective paper, paper two, the structured paper, and paper three, the lab paper. So your practical paper will be converted to 30 marks. Okay. So bringing these three into a total of 130. Okay. And since Cambridge has published the recent grade threshold, we should also need to talk a little bit about the grade threshold. Because at the end of the day, we operate based on, I was going to say our boss in Cambridge, but yeah lah. So the grade threshold has already been published. Later on, I will download and throw it into the Google Drive, the general folder where I put all the mark scheme and question papers. Okay, so if you look at the grade threshold, you'll probably be looking at either BY1 or BY2. So it depends on which paper tree you set. So the grade threshold is now sitting at 201. And then maybe if you take another variant, then it will be 204. Okay. So if you're aiming for an A star or an A, knowing where the grade threshold is helpful because you also need to add this in with your A2. So when you sit for your A2, you'll have paper 4. Currently, we're only doing paper 4, right? So hopefully you have already started practicing your paper 5. You can use the videos on the channel for that kind of help. And also, if you really want to, you can submit to me your paper 5. A few lah, not all. I can mark for you. Okay? Just submit and tell me what year it's from. So this one is 30. The total is still 130. Okay? So that means in total, right, the big total would be 260. So out of this 260, if you want an A star, I will give you two types of numbers. One number is called a confirm A star, meaning it doesn't matter how smart the students are or how smart the cohort is, you are more or less confirm an A star. There will be no year where I see 210 and right beside it, I don't see A star. Okay, so you could say, well, I could lose 50 marks. Yeah, lah, you can lose 50 marks, lah, but how many marks have you lost in your AS is the question. Okay, and then this is probably an A star is around 205. 200 also can sometimes. So sometimes, depends. You could get like 197, 196, who knows? Okay. But most of the time for the Asian countries, like this side of Asia, the East Asia, Korea, Japan, Hong Kong, Malaysia, Singapore, Vietnam. So in this side of Asia, the East Asia, most of the time is 200 something. Okay. All right. So number two, because the same level of time zone will have the same paper. So probably our paper variant is the same as Hong Kong or Vietnam because the time zone is plus minus 2 hours. So we should be sitting for the same paper. If let's say the time zone is like 5 to 6 hours and you're in India or Pakistan, then maybe you will sit for a different variant. The grade threshold will shift. Okay. So for A, if you want to confirm, meaning come hell or high water, you want to get an A, then it's 180 though. Confirm already. You don't have to worry. Okay. And then probably we'll get an A is around 175. So, and then if you just want to pass, look, Bs can get you into most universities already, unless you're talking about Ivy Leagues. Okay, so there's nothing wrong with getting a B. B is a solid grade also. So this one would be 150. This one is 155. Sometimes this one can drop to 1451. It depends on the student. the statistics. So around 150 lah. Hey, you can lose 90, you can lose 110 marks. Okay. So don't get discouraged if let's say you didn't do so well in your AS. Most of the time, if you check your university application, B is enough. They want maybe 3 Bs or 1A, 2 Bs. Okay. So factor it accordingly. As I've mentioned before, studying is not always straightforward or easy. So don't compare yourself with other people. Compare yourself with how much more you need to get here so that you can get the grade, so that you can go into the university that you are okay with and the course that you are okay with. All right? Don't be too hard on yourself. Okay, so I don't know what your raw mark is. I mean, later if individually you want to DM me, I can comment a little bit on it. But it sort of depends on what grade you're looking for and also how much time you can use to prepare for your paper 4. Because right now, everything is hinged on your paper 4. Okay, so take a screenshot of this if you need to. Generally, A and B is okay. C is also fine. Certain universities, 2B, 1C. Okay, 3Cs also got. All right, so it's okay if A level is a very exam-based system and it's not for you. Choose a university that is more practical-based. In fact, practical skills are more important than theoretical skills in real life. Okay, so do what you can. Right, so that's the first thing I want to talk to you about. Second thing that we're going to do today is we're going to first practice some parallel plate electric field questions, and then we're going to look at some capacitors. So I think I've already prepared the questions, but they look kind of small on my screen, so I'm going to print it out separately. Give me a sec. If you have any questions regarding the grade threshold, feel free to ask. I think what I want to do is I won't touch the capacitor question. In fact, I won't touch the paper that is just released by Cambridge. I see circular motion. Okay, I won't touch the paper that's released by Cambridge because I want you to have a full set of paper that you can try, hopefully under exam condition. Okay, so maybe when we are closer to the paper, we can discuss the questions. But yes, I want you to have a full set of paper that you can try. So I will not be discussing the summer 23 papers. At least not until we are ready. Okay, but we can look at the one from winter 22. Just want to check in on the parallel plates. So if you remember from the previous class, when we talk about the electric field cases, I've already explained that we looked at a single charge, double charge. Here are some questions to try. Since nobody asked me questions, I assume you're okay. If you haven't tried, it's not good to assume that you are not okay. So go try. It's okay to ask me belated questions. So case 4 is the one that is regarding parallel plates. Okay, so parallel plate is supposed to be the easier question because it has something to do with uniform field or constant field. If the field is constant, we no longer need to use the Coulomb's law equation that KQQ over 4 pi epsilon naught square is not really needed anymore. Okay, So what we actually need to apply is actually the definition connectors. By definition connectors, I mean, number one, to calculate the electric field, we will use V over D, which is the potential gradient. Okay, so if you look at the four pillars, it's the four pillars. Yeah. If we look at the four pillars, to find E, we use V over R. But R is actually the separation between the charges. So from V over R, it became V over D. Okay. And we also use this other connector. Electric field is force per unit charge. So if you look here at this connector, electric field is force per unit charge. Okay. So basically, we don't use the red color box. We use the highway, the bridge in between it. And finally, electric potential energy would be Q delta V. And as usual, as mentioned before, we will use this one, this connector. So for parallel plates, right, we don't use the box. We use the connection in between the box or the four pillars, right? So I think I'll do a few quick ones with you. Let me print it out. Starting with page 41. I think put it here. Okay, as mentioned before, because it's new, so there's not that many parallel plate, but if it comes up, the questions are relatively doable. Okay, so this one starts off by similarly asking us what is indicated by the direction of the electric field line. So the direction of the electric field line will always point towards the direction of electric force. Force acting on a positive test charge. So 1 mark for the direction of electric force, 1 mark for the idea of positive test charge. Okay. So in 4B, here you have a parallel plate, with potential difference 2400 volts, right? And you're asked to draw 5 lines to represent the electric field in the region between the plates. So during the exam itself, do try to separate them evenly. Okay, so what I'm going to do is I'm going to start splitting. They want 5 lines, right? So I just divide by 2. Of course, right now I'm judging by eye, but during the exam, if you have a ruler, that will be better. Okay, so I already have 5 lines, more or less evenly distributed. And the direction of the force on the positive charge will be pointing downward. So from high potential to low potential, direction of this line will be from high potential 2400 to low potential. Or you can imagine if I have a positive charge, the positive charge will experience a force in this direction. Okay. Okay, next. Calculate the strength of the electric field between the plates. Let me close some windows first to decrease the lag. Okay, so to find the electric field between the plates, what we're going to do is we're going to use the equation E is equal to, you can either use F over Q, or you can use E is equal to V over D, or the change in potential between and the plate separation. I do not have the force. Neither do I know what charge I put inside. So obviously not the first one because we don't have enough information. But we can use the potential difference between the plates, 2400 minus 0 volt, because up here is 2400, down here is 0 volt, divided by the plate separation, 4.6 cm. So as usual, everything here should be in SI. So from here, I will have 52174. And I'm going to convert this to 2SF to follow the question. So 5.2 times 10 to the power of 4. Of course, you could also write in 3 significant figures, but no more than 3 lah. All right, because the raw data is 2SF. Okay, next part. A moving proton now enters the region between the plates from the left. So this moving proton is, you kind of have like a fixed electric field. It's the same electric field, okay? And the proton is now going to enter here. And obviously, because this proton is positively charged, it will deflect towards the lower plate lah. And I'm guessing they're going to ask you to draw. Oh, yes. Draw a line to show the path of the proton as it moves through and out of the region of electric field. So it has to go out, okay? So it would not collide with the plate. So what will help me is if I draw a horizontal line, this is the line where the proton will move if I turn off the electric field. So meaning I turn off the electric field, there is no more forces acting on the proton. And then this is the direction that the proton will travel. Due to its inertial property, it will move in a straight line. Okay? But because there is a force, and we know that the direction of the force is pulling it here, the electric force will be pushed away from the positive top plate. So it will push the proton away from the top plate. This means that the proton will deflect downwards, and you need to draw it in such a way where its exit like leaves the plate lor. So if you draw like that, not wrong, just not what they want. So apparently this one actually will leave the plate. Okay, so then you need to corner slower. So the very slow, gradual way, this is a parabola, it will exit the plate. So start turning, something like this. So if you turn in the right direction, you get 1 mark. And then if the shape of the field is correct, you will get another mark. So downward is 1 mark. Then the shape. It's supposed to be parabola. So it cannot be a straight line. It cannot, look like a circle. Although at this scale, it's hard to tell a circle and a parabola apart. So something like this will do. The general shape, we obviously judge by eye. Smooth curve can now. And also, parabola inside the electric field. And then outside the electric field, it has to be a straight line. Okay, so parabola inside the electric field. And then it's straight line outside the electric field. So I could make it a bit more obvious. Here would be a straight line. No more curve already, okay? Of course, if you can use a ruler to make it extra straight, that would be helpful. So this part is 1 mark. This part is 1 mark. All right. Next, a helium nucleus now enters the region of the electric field along the same initial path as the proton, traveling at the same initial speed. State and explain how the final speed of the helium nucleus compares with the final speed of the proton after leaving the region of electric field. Well, the helium nucleus is 4 times heavier. 4 times the mass of a proton. All right, so let's compare 4 helium and 1 proton. So the mass is 4 times. 4 times of this. And the charge is 2 times of this. Okay, so this means, right, if I think about F is equal to MA, because this is QE, F is QE, QE is equal to MA. So this is for proton. Later we will need to write an explanation, but this is for proton. But then for the helium nucleus, instead of Q, we will have 2QE. And instead of m, we will have 4ma. So obviously you can tell that the acceleration is less, right? You can tell, right? Because your force is double, but your mass is 4 times. So you accelerate half lah. You accelerate less. Okay, so this is the first thing I'll say. I would say that the helium nucleus has double the mass. I mean, double the charge. Double the charge of proton, but 4 times the mass of proton. Hence, the acceleration of helium is less, and because of this, the final speed is lower for helium. Compared to the final speed of proton. If you think about it, at the same time, you also need to mention both helium and proton has the same initial speed along the same path. So that's why I can say less acceleration means the final speed is lower. So first mark is when you mention that here is how we judge the evidence that the acceleration is less. So I need to mention that double the charge, but 4 times the mass. Okay, so when there's double charge, it means there is double force. Okay, so you can add that in if it makes it clearer for you. Double force, so twice larger acting on helium, but there is 4 times the mass. So the thing that is pulling on is 4 times more massive. The next mark is when you mention the acceleration of helium is less. And the reason why the acceleration of helium is less, and this allows us to deduce that the final speed is lower for helium. So this is 1 mark. And then you also mention that the initial conditions are the same. Final one is 1 mark. Of course, if let's say the helium is already moving faster than the proton, then we need to redo the calculation. So you can think about it from the perspective of V square is U square plus 2AS, right? So if the initial U is the same, then larger A means larger V. But if your initial U is bigger, then maybe it will counterbalance because you didn't accelerate from the same initial speed. So you should also mention that the initial speed is the same. All right. So a heads up here for parallel plates. You can use, I mean, they can ask you to calculate. They won't because using the equation is already tested in AS, but they can. Or I wouldn't say they won't, I would say it's unlikely. But for parallel plates, because E and F is constant, you can use the equation I used just now. F is MA, QE is MA, so A is equal to QE over M. But because F is constant, A is also constant. You can calculate using this equation, meaning your Stuva equations can be used. Your equations of motion, like the one I quoted just now, V square is U square plus 2AS. S is UT plus half AT square. All this can be used, provided for parallel plate only. If it's the point charge or the charge sphere, then cannot. All right, so this is an example of a parallel plate question. I don't think it's too difficult. It's also a lot of marks. So if they ask you, then you just substantiate accordingly. Okay, so we're going to move on to capacitors now, right? And I want to do a recap on what capacitors are, and also the important things you need to know for capacitors. Okay, so I think I'm going to use the newer notes. So capacitor recently, by recent I mean in the past new syllabus refresh in 2020, has experienced addition of the charging and discharging mechanism. So we want to look into that slowly, okay? But at first, capacitor, you definitely expect a question. It can be linked to obviously chapter 18. So here are some possible uh, links or topic combo. Can be 18. I mean, they can ask you 18 and 19, which is a capacitor and electric field. Or they can ask 19 and 20, 21, alternating current. They can also ask 19 and 20, magnetic field. So basically, 18 all the way to 21 is one big family. 18, 19, 20, 21. Yes. Most of the time, the obvious link is between 18 and 19 and 20 and 21 lah. But it's like a combo. It's like the mechanics topics, work, energy, power, forces, kinematics. We can mix them up together, okay? Because they're all about electric and magnetic fields. So when you expect to study this, we generally expect about 30 to 40 marks out of 100, 30 plus lah, okay? Out of 100. So it's a pretty extensive topic. Okay, so don't let it go. Anyway, 19 is one of the easier topics, okay? So first, when you want to think about 19, think about all the things that you've studied in circuits, okay? And think about how this is just a easier or simpler version of circuits. Because in circuits, right, we study a lot of strange bridge connection lah, potential divider lah. But because this capacitor is a new thing, capacitance, so we are going to go back to level 1 to study what is a capacitor and also what is its role in the circuit. Okay, so we define capacitor as a charge stored in a single plate. If you want to find this one is in the topical notes. All right, because it's recently been updated. And by recent, I mean I think a few weeks ago, few months ago. So I'm going to write them together with you. Okay. So we define it as the ratio of charge stored on a single plate. So in one plate, or one single plate of a capacitor to the potential difference across the capacitor. Okay. So to build a capacitor, we will need a bunch of parallel plates, okay? And whenever we take the charge stored, we take one plate only. So from here, we can see that capacitance can be defined using the ratio of Q over V. So capacitance C is equal to Q over V. Very much like its analogous resistance. Resistance R can be defined as the ratio of V over I. So in circuit, we use ratios to define a lot of stuff. But what we have normally when it comes to a capacitor is we will have some, I mean, normally what we do is we'll connect or we'll apply a potential difference across this one. So probably we'll connect this to a battery or a power supply. Maybe this is 9 volt. Okay. And then because this is positive terminal, so the charges will begin to move. The negative terminal will make one plate negative, and the positive terminal will move all the charges and make the other charge positive. So that means on this plate, right, the charge is, let's say, negative 100 microcoulomb. Then this charge here would be positive 100 microcoulomb. And depending on how much potential difference I put, as long as the capacitor didn't burn within reason, I'm going to get straight line passing through the origin. This is the graph of Q against V. So the more potential difference I apply, the more charges will move so that we can, separate the charges between the positive and the negative plate. Okay, so from the equation, Q is equal to CV because C is Q over V. There, the equation, the definition, C is Q over V. So Q is equal to CV. If they ever give you this graph, you can use the equation to help you see that the gradient is equal to C. Okay, so what are the factors that will affect the capacitance, just in case they ask when it comes for explanation? Capacitance is proportional to area. Kind of makes sense, right? Because this capacitance here shows the ability or the ease to store charge. So the bigger the capacitance, the easier it is for the parallel plate or for the system to store charge. Just like the larger the value of resistance is, the better the resistor is at blocking current. So it's the same idea. Capacitance, the main purpose is to store charge on one plate. Okay, so the larger the capacitance, the better it is at its job. Of course, it's inversely proportional to the plate separation. So let's say the separation here is X. The further away the plate is, the harder it is for you to induce charges to create an electric field in between. Okay, and then finally, the type of insulator in between the plates. I think if you need a conceptual understanding, I'll write that down for you. If C is proportional to A, will be like larger area, more charges, more charge stored. Okay, and C inversely proportional to X. When there is a smaller gap, there's a stronger electric field. Okay, the equation E is V over D, or in this case, it'll be V over X. So the smaller the X, the stronger the electric field, more charge I can put on the plate. Okay, finally, type of insulator between the plate. Sometimes we just use an air gap, but sometimes we're going to put something inside, like a sandwich like that. So we sandwich an insulator here. Sometimes we use a ceramic or a dielectric. This one is not covered in your syllabus, but just know that later if you do more engineering stuff or circuit stuff, I can manipulate the type of insulator in between the plate because it tells me how easy it is to set up electric field. Okay. So finally, uses of capacitor, sometimes they will ask, you just memorize a few. It's used to store electrical energy, not charges. Because they didn't really store charge. It did store charge on one plate, but what they did was just separate the charge. Take the negative charge from the positive plate and put in the negative plate. Okay, so it can be used to block direct current because once the potential difference across the plate is 9 volt, the amount of charge stored is fixed, 100 microcoulomb. So current will not flow anymore. We'll talk about this very soon. Okay, so it can be used to block DC. We can use to smooth the ripple of direct voltage or currents during rectification, during alternating current rectification. This one we'll see again in chapter 21. And we can also use it as a timer because we can use the discharge equation. A good example is like your camera timer. Whenever something flashes, it takes a while for the capacitor to charge up. Okay, so depending on the time, I'll be able to get a slightly different variant. Okay, so we're going to start by looking at all four types of the users and also teach the others, the remaining subtopic. Let's start with storing electrical energy. Okay, and as usual, screenshot, or this will be in Google Drive after the class. So energy is stored in the capacitor because when you think about this circuit, when the switch is closed, okay, I'll put a switch here. When this switch is closed, call this switch S. Okay, so when the switch S is closed, work is done by the power supply, by the 9-volt power supply to separate the charges. Because what the 9-volt does is it's going to take the energy from one plate, and I mean the charges on one plate, and put to the other plate. Because before I connect, the plates are neutral. And once I connect, all the electrons will be moved because the battery is like, I need your potential to be the same as mine. Okay, it's a little bit like when you open a dam and then the water start to pour out. Okay, yeah. So the energy from the power supply is stored in the capacitor as electrical potential energy. Another way of thinking of it is like when you charge your phone or your devices like your iPad or your laptop. Most mobile devices these days, we use capacitive charging, meaning there is a capacitor inside your phone. When you plug your phone into the power supply, what the power supply does is they take all the positive charge and negative charge inside the capacitor, rearrange to put all the negative charge on one side. And then when you unplug your phone or your devices, then the negative charge will flow back to the positive plate slowly. And because the charge is flowing, there is electricity. Because it's electricity, you can play your games on your phone or you can use your electric devices. Okay, so I want to talk a little bit about this area under the QV graph. Okay, so if you think about the graph of Q against V, I've already drawn one there. But to find electric potential energy, E was Q delta V. Or if you are not afraid of the calculus form, it's the integration of Q dV. But thankfully, we know the equation to find the area under this graph. So let's say your potential changes from 0 to 9. This area, let's say this is Q, and this is V. This area E will be equal to half. Okay, let's not use 9. Just use an unknown or a variable. So it can be half QV. But also at the same time, Q is equal to CV. So the energy stored can be half CV square. If I substitute Q, it can also be equal to half Q square over C if I substitute V. V is equal to Q over C. So V square is Q square over C square. One of the C will cancel out. This one is kind of important because the capacitor's main function is actually to help us store. It is actually a form of battery or a power supply. So this one is the energy stored in the capacitor. Okay. So at the end of the day, right, what is going on is I place the charges separately as a temporary stopgap. And because the charges are like stuck here, it cannot flow back. So whenever we discuss this, we will always say that the capacitor store energy and not charge. This one, sometimes they will ask you to explain. Okay. So we know that the charges on both plates are equal in magnitude, but opposite in polarity. So let's say this is my plate. One plate, I'm going to draw 2D, okay? One plate will be maybe positive Q. The other plate will be negative Q. So hence, there is no net charge. Charge is not stored, okay? But energy is stored because there is a charge separation. Before I connect to a power supply, the charges here are neutral. Same amount of positive and negative charges. Once I connect to a power supply, the power supply will start taking the electrons from the positive plate and moving the electrons to here. So the electrons will move to the negative plate. That's the role of the power supply. Okay. So this is due to the work done by the power supply. But I should also mention the work done by the power supply or the energy of the power supply is actually calculated using the equation E is equal to QV because the power supply has constant voltage. Okay. Whereas the voltage inside the capacitor will increase, right? So let's say, for example, this is 9 volt, and then this one is potential difference across the capacitor VC. VC actually takes time to increase to 9. That's why the energy stored is not as simple as just multiply. Okay, so the easiest way is to look at this one and look for area under the graph. It's a bit like when I put the first charge, oh, very easy lah, because the plate is empty or neutral. When I put the second chunk of charges, it's going to take me more and more and more and more energy. The area is more and more and more. It's so a lot like elastic potential energy. The more you stretch the spring, the harder and harder it is for you to stretch the next cm. You need more and more energy because the spring is already stretched. All right. So energy stored in the capacitor is this one. Footnote that I'll write close by here would be the energy given by the power supply. This E is actually equal to QV. Notice that it is not the same as the energy stored. Then where is the lost energy? Well, dissipated as heat. So the energy of the supply is bigger than the energy stored in the capacitor. And the reason to that is because this is due to heat loss during the charge transfer process. So heat loss in the connecting wires. So as a current flow, there is some heat loss. If you hold on to the circuit, if you ever had a chance to do an experiment involving the charging and discharging circuit, then you will realize that it is hot. The capacitor get hot. You charge your phone will get hot. The charger gets hot, you know, the adapter, the phone plug adapter also gets hot. Okay. So this is the thing that you should know about the capacitor. We're going to move on a bit. Before I talk about that, I think it's a good time for us to just write down what is a charging mechanism. I've already mentioned just now, but here's an example for you to look at. Let's say, anyway, this is page 3. Let's say you have an EMF E, the ammeter, and then resistor R, capacitor C. So before I close the switch, both plates are neutral. There's no current in the circuit. Okay lah. Nothing much to talk about. Okay. Then I close the switch. When I close the switch, right, there will be current flowing in this direction through the ammeter. Okay. And let's say I'm going to label the plates for easy discussion. This is plate A and this is plate B. Okay. So in order for current to flow in this direction, this means that electron must flow in the opposite direction, right? So electrons in plate A will leave flowing in the opposite direction, pass through the resistor, lose some energy, and then be deposited on plate B. So eventually, plate B will become negatively charged. Okay. And because this is already negative, whatever electrons that was initially at plate A, due to the pull of the power supply, power supply here is positive one. So due to the pull of the power supply and the push from the nearby plate B, will become more and more positively charged. Okay, so making it more positive. Current will flow in the circuit, but not through the capacitor. Between here, there is no electron flowing. So eventually here, you will get negative Q. So it will store a charge of negative Q. And if let's say I put 10 electrons in plate B, I would have removed 10 electrons from plate A. So plate A will be positive Q. Okay. And what happens to the potential difference between the plate? Okay, maybe I'll change color for this one. Hang on. During this process, the potential difference is increasing. Will it increase forever? Obviously not. This scenario will continue until the potential difference across the plate is equal to the EMF of the power supply. So if let's say this is 9 volt, and then once I put enough charges here, and I put enough charges here, the potential difference will be 9. So here to here will also be 9. Okay. When this happens, current will no longer flow. There will be no more potential difference inside the resistor anyway. So this current will zero. So there's no more charge flow, and current measured by the ammeter is 0. The capacitor is fully charged. And if you want to find the amount of charge stored in the capacitor Q, Q will be equal to CV. Now you can use Q is equal to CV. This V is equal to 9 volt. Okay. So far, whenever we do capacitor, we already close the switch, it's already fully charged. But just know that it may take some time. Okay. And we don't study the equation of the charging process. We just study the theory of it very briefly. But we will use the equation for the discharging process here. Because now if I remove the power supply, remember here we have a bunch of electrons. And the electrons, they don't like each other. They don't want to sit on the same plate together. They are like, I don't like you electron. They will repel each other. So the electron will begin to backflow like this. So electron will go back. Bye. See you. Making this plate more neutral. So what happens to the value of Q? Again, it doesn't really matter which plate you are looking at, positive or negative Q. Let's say we just take the magnitude only in Coulomb and T in second. We're going to expect to get the charge will decrease and eventually it will drop to 0. And normally this is the initial charge. I will call this Q naught. Okay. So the question would be, what is going on here? Why does the PD across the capacitor decrease exponentially? So personally, I find this question very mathematical But they did ask, so I'm going to list down the question year where it came from. Question 6. Okay, so right now Q will decrease exponentially because logic, right? That's the time, as time passes, there's less and less charge. So because there's less and less charge, charge will flow slower and slower. The derivation of this is actually a first order differential equation. And differential equation is not part of your syllabus, so or at least not part of the physics in your syllabus. So I'm not going to hurt our brains by doing this, okay? So we have to just accept charge, right? So initially, the PD across the resistor is equal to the PD across the capacitor. So right now, if you see there's a resistor here, sorry, I didn't label our little R. This is the resistor R, this is C, okay? And we know from V is equal to IR, the current in the closed loop causes the charge on the capacitor to decrease or to lose charge. But charge on the capacitor is proportional to potential difference. So potential difference decreases. Okay, so if you need an equation, the first one is self-explanatory. When the capacitor begin to lose charge, okay, the current will flow, and then the charge of the capacitor will decrease. For the second one, Q is proportional to V. Okay, because Q equal to CV. And because of this, over time, the potential difference, the charge on the capacitor decreases. Sorry. Over time, the charge stored on the capacitor decreases as PD decreases. So this is basically just saying that right now I have two graphs. I have the Q graph. Why does the V graph also decrease like that? Okay, it's only a 2-mark explanation, but we also kind of don't want to be blindsided by it unexpectedly. Okay, so I would say if I want to find the potential difference across a capacitor, I'm going to also use it as a reading for the potential difference across the resistor. Actually, out of these 4 points, you only need to write 2. All right, so the most obvious one is we expect the potential difference to drop because current will drop. V equal to IR. So current will drop. When currents drop, capacitor will lose charge. Charge is also proportional to V. So Q and V should have the same shape of graph. That's why over time, charge stored on the capacitor decreases, PD also decreases. Okay, if you want to, you can also, remember the QV graph. This is the third time I draw the QV graph. Proportion. All right. Second thing you need to know is the equation. So if I pull up a question paper, where's my question paper? There we go. The equation of the capacitor charging and discharging is actually given to us. You are given this discharging of a capacitor. It looks like that. So we need to be able to modify or adjust this equation. This X and X naught can be anything. It can be Q, it can be I, it can be V. So in other words, it can be rewritten as Q is equal to Q naught E negative T over RC. I is equal to I naught E negative T over RC. For the purposes of your syllabus, the derivation is not needed. You just need to know how to use the equation. Okay, so V is V naught E negative T over RC. Okay, so everything in this row are initial values. Okay, T here is the variables are obviously your charge and your time, or your current and your time, your voltage and your time. R is the resistance in series with the capacitor. C is the capacitance. Okay, so this RC is actually a constant, and we like to call it the time constant. So it's like a constant in your equation, depending on how I arrange the circuit. All right, so we need to define the time constant. Time constant symbol is actually tau, same symbol as torque. So time constant is equal to RC. RC is the time taken for the capacitor to discharge to not half, to 1 over E. I don't know why I don't remember why it's 1 over E. Hang on. 0.66. 1 over E. 0.3637. 37% of its initial charge or voltage or current. Okay, charge is easier. All right. How did I get this? Well, let's say I borrow Q is Q naught E negative T over RC. I will let T be equal to RC. So if the time taken or time that has passed is RC, RC over RC is -1. So 1 over E. So the charge is now 0.37 Q naught. A graphical representation would be, if this is V, this is 0.37 V. It's a little bit like half-life, but we don't take 0.5. It's not half. This one is RC. Okay. So 37% instead of 50%. Okay. So how does it affect the time taken to discharge? Well, R obviously affects how quickly the current flow. Okay. So this one affects the charge flow or the rate of charge flow. And C affects the amount of charge stored on the plates. If I got more charge stored, obviously I will need a longer time to discharge, right? More charge to throw away from the plates. Okay. So this charging and discharging is fairly new. We'll do some questions after the break. But the last thing I want to point out, okay, is in page 2. I'm not really going to talk much about the capacitor in series and parallel, okay, because I think in recent years it has taken a backseat compared to the charging and the discharging. But just in case they decide to ask, okay, the ideas are very similar to resistors and circuit. Okay, so the only difference is that the identity has changed. So if you look at the lecture video, we will derive the identity for you. But today I want to point out a few things. Number one, if you have capacitance in series, the charge is equal. Okay, and then the voltage is shared. For parallel, the charge is shared, the voltage is equal, like resistors. Okay, we can do some questions later if you need to. So you can look at the video. All right, which means if I look at the combined capacitor in series, cause the total capacitance to decrease. Because right now I got more and more capacitor to charge because when I charge one, I have to charge all. since the charges is equal. So this means the total capacitance will decrease. For parallel, the total capacitance increase, because I just add them up. All right. And finally, because capacitance is defined as the ability to store charge, okay, we can also find the capacitance of an isolating conducting sphere. Let's say I have a sphere where I can park some charges here. And then if I put a voltmeter here to measure V, which is the potential difference on the surface, again, the charge stored here is positive Q. For the don't know how many time, if I plot Q against V, I'm going to get this shape. Okay, so let's say I start Q equal to Cp. And V is the potential difference on the surface. But also at the same time, V is actually equal to the potential difference on the surface is equal to Q over 4 pi epsilon naught R. So I can actually substitute this in. Q is equal to C bracket Q over 4 pi epsilon naught R. I can cancel the Q. Okay. So finally, if I want to find the capacitance, capacitance is equal to 4 pi epsilon naught R. Okay. Capacitance is proportional to the radius. This is for a charge sphere. So this is the bridge that ties it back to chapter 18. It's not super popular, but it has been asked before. If you want to know which year, I think the kept some from the older years. This one and this one. Okay. So a lot of things. Let me summarize. 1. Capacitor is a parallel plate. We must know how it charges. I've spent some time talking about the charging mechanism, how it discharges. And we're going to use the equation X is equal to X naught E negative T over RC. As usual in physics, we want to be able to achieve 3 skills. We want to be able to calculate, so we should know the equation of the relevant idea. We want to be able to explain, so we know the words of the relevant idea. We also want to be able to graph. Obviously, they're all linked together. Okay. Mainly, capacitance Q can be defined as CV. Okay, so when you discharge a capacitor, let's say I draw a discharging capacitor, there will be a resistor here. C, this is R. Okay. Second thing you need to know is the capacitor in series and parallel. Okay. And finally, the third thing you need to know is the capacitance of a charged sphere. And some basic explanation stuff. So charged sphere one just now was C is equal to 4 pi epsilon naught R. The basic explanation ones are uses of the capacitor, already listed down in the notes for you. Uses of the capacitor, why it store energy. E is equal to half QV and not charge. And finally, the explanation of this graph. Explain why Q and V, same graph, have the same shape. Okay, well, these are the explanations. This is a chapter actually. The problem with people is that they don't really understand the charging and discharging mechanism. So when the question is twisted a bit, we feel a bit stuck. So I'm going to give you some time to take a short break and to digest your questions. But When we come back, we will do the more recent capacitor charging and discharging questions, starting from Feb March 22. We want to do the recent ones. So in the meantime, if you have anything you want to ask, or if you encounter any kind of strange capacitor questions, feel free to request in the chat, right? We'll take a 10-minute comfort break, and then we'll come back and do some questions. But the chapter is over already. We can start with this one. All right. See you in 10. Let me stop the recording. Sometimes when you study past year questions, right? Okay, the examiner report is probably as important as the actual mark scheme itself. But I will only look at the examiner report if the question is interesting. I mean, sometimes you can learn some stuff, and sometimes they will just say students, candidates find it difficult to answer the question. Okay, lor. All right. So since we're back, I want to let the brain cool down a bit. Just want to show you some general recommendation from the ER. I think a lot of it I have emphasized pretty frequently. So for example, per unit should be used when the quantity is the ratio. Okay. So for example, just now when I define capacitance, I define it as the ratio between two quantities. Okay. You can even say charge stored per unit voltage. Don't use the word divide. You can use the word product. Don't use the word multiply. Okay, so you got a lot of general comments, and every question there is a comment one. For example, here it says that, well, common errors are the confusion with the number of molecules and number of substance for the PV is equal to nRT, and not being clear with T being the thermodynamic, underline some more temperature. Okay, so I just want to point that out as we move forward. As you do your past year questions by year, it's probably good to read the examiner report, especially if the question looks a bit strange. All right. So we're going to start off first by looking at maybe something a little bit easier. We're going to look at Feb March 22. And then I'm pretty sure I printed that one out also for you. And extend and make everything big. Okay. So we're going to look at Feb March 22 P42 first. So here is the QV graph of a capacitor, the one that I've drawn many times. Okay. And it says here, whatever this capacitor is, if I put 4 volt, I'll get this much charge. If I put 12 volt, I'll get 1.8. So from here, I can map out what is the charge stored just based on the graph. Okay. This capacitor is connected to an 8-volt power supply. Beautiful. And 2 resistors, there's R, there's S. Okay, don't panic. Look very okay to me, the circuit. Resistance is 25. Resistance of X is 220. Switch can either be in the position of X or Y. Okay, let me tell you what happens first. When we are in the position of X, the capacitor is connected to the power supply, right? So at position X, the capacitor is charged because it's connected to the power supply. At position Y, here, when it's not connected to X, this capacitor is discharging. How do I know? Well, there's no power supply. And then basically the capacitor can home run back to the, if this is positive, this is negative, this plate will be negatively charged. The negative charge has a direct way to go home. Negative charge is like, yay, let's go home to meet our positive charge. Okay, so at Y, it will discharge. So a way to look at it is A, is there a power supply? And if it's charging, there's always a connection to the power supply. Okay, and then if you want to know whether it's discharging, Is there a route or a pathway or a loop for the current or the electron between the plates? So the electron can go from the negative plate to the positive plate. Okay. Right. Wonderful. Let me just yoink all of this away. Continue reading the question. The switch is in position X so that the capacitor is fully charged. Beautiful. Calculate the energy E stored in the capacitor. Okay, so E can be seen as half QV, or if you want to, area under the QV graph. So I'm going to go back and look at this. Of course, you don't happy go and take 12 lah, hello. Okay, if it's fully charged, then the potential difference here is 8 volt. The potential difference here will be 8 volt. No more current will flow. The potential difference here is 0 volt. In the beginning, VR plus VC is 8. So in the beginning, it will probably look something like 8 plus 0 is 8. Then you will reach 7 plus 1 is 8. And then eventually you will reach 1 plus 7 is 8. And then 0 plus 8 is 8. So the capacitor voltage will increase until it's 8. When it's at 8, current will stop flowing. The resistor voltage will drop. Okay, that's the idea. So when this is fully charged, the potential difference is 8. We got to read 8, my friends. This is 8. This is 1.2. This point here. Okay, so we're going to look for the area under the graph, the triangle, or we will use half QV. If you make the rookie mistake of taking the extreme points in the circuit, then maybe stop doing it, because question is full of gerbates. So the charge stored is 1.2 times 10 to the power negative 4 coulomb. The voltage is 8 volt, because the power supply is only 8. So from here, you will get 4.8 times 10 to the power negative 4. You have ideas to use half QV or area under the QV graph, you get 1 mark. The final answer and the substitution is 1 mark. Okay, switch is now moved to position Y. Show that the time constant for the discharge circuit is 3.3 seconds. Tau is equal to RC. Okay, so in the discharge circuit, if I look at the, okay, I'll tell you what, let me crop the circuit over. I look at my circuit. Here, the discharge circuit is the bottom's part. So instead of taking resistor resistor R, you should be using resistor S. Okay, so the discharge circuit is this one, this loop. So this will be 220 times 10 to the power of 3. Wait a minute, do we have the value of C? You may be thinking, no, Watcher, they never give me the capacitance also. Well, you gotta trust yourself. If they never give you, you can find. Because also Q is equal to CV. So C is Q over V. So meaning here I can put Q over V. 220 times 10 to the power of 3. The charge stored, I can copy. I just read the graph only. 1.2 times 10 to the power negative 4 divided by 8 volt. I believe this is 3.3, but I shall double check using my calculator first. Divide by 8. Wow, exactly 3.3. Chef kiss. 3.3 seconds. We substituted it into this C. Okay. The fully charged capacitor in A stores the energy E. Okay. Find the time taken for the stored energy to decrease from E to E over 9. So maybe I will go to my formula sheet and copy this equation first. X is equal to X naught E negative T over RC. And then I remember my teacher said, well, this X can be anything. Well, I did not say anything, okay? I said this X can be V or I or Q, not energy. Don't do it, not energy. Okay, so right now, this means I either need to find V or I need to find Q when the energy decrease from E to E over 9. Okay, so I'm going to write down the equation for energy, starting with what I have. E is equal to half QV. Do not recommend using this equation because they are both variable. When Q change, V will change. They're both variable. I prefer an equation with constants, with at least one constant. Cannot have all these three is variable. My brain very pain, okay? So I'm not going to use this. I'll use the other one. Maybe I'll use E is half CV square. Praise be. This half C is constant. And we like constant in our lives, okay? So from here, you can see that E is proportional to V squared. Because C is constant, right? So this is my first step. E is proportional to V squared. Based on the equation, E is equal to half CV squared. So because of this, E divided by E over 9 is equal to, the initial voltage is 8 volt, divided by new voltage square. Okay, 8 volt divided by new voltage square. So from here, I will get 3, because this is 9, right? So square root of 9 is equal to 8 over V. V is actually equal to 8 over root 9. Why is so extra? Root 9 is 3. 8 over 3 volt. Teacher, your final answer is fraction. This is not my final answer, so you can leave it that way. You don't want to leave it that way, you press calculator also can. I'm just going to leave it that way, okay? Next, step 2. Then I use this equation because I can use V is V naught E negative T over RC. So the V is 8 over 3. The V naught is 8. E negative T over RC. I'm going to keep it this way so I can cancel my 8. Or you press calculator also can. That's fine. So finally, I will have 1 over 3 is E negative T over RC. Bring the E over, ln 1/3 is negative T over, we have RC, right? RC is 3.3. Okay. So press calculator lor. T will be equal to negative 3.3 ln 1/3. The negative should go away because ln 1/3 is negative. So I'll get 3.62 seconds. Okay. So the important thing when using this equation is, although X and X naught can be anything, I don't mean anything, okay? It's either voltage or current or charge. If it's not these three, like for example, energy, then you will need to use the energy is equal to, CV square or Q square over C, so that you can find the proportionality and use the proportionality ratio to find the new potential. And once you have the new potential, then only you sub inside. So meaning when the energy dropped from E to E over 9, the potential difference will have dropped from 8 to 8 over root 9, or 8 over 3. Okay? All right, part C. A second identical capacitor is connected in parallel to the first capacitor. So as mentioned just now, whenever we connect some capacitor in parallel, the total or the effective capacitance increase, but it's identical, so it's double. Okay, so for example, C and C, because they are in, oh no, wait, parallel, I say, like this, C and C. So the total capacitance is C plus C, double or 2C. So how does it change the time constant? Well, obviously, the total capacitance is doubled. Teacher, must write double, cannot write increase, cannot lah, because they say identical. If they say another capacitor, but they never give you any context, is this capacitor the same 2 times, 3 times, 10 times, never tell you, then sure, you just say increase. But if it's identical, then we know it's doubled. If the total capacitance is doubled from time constant is equal to RC, time constant is also doubled. So when the time constant is doubled from 3.3 to 6.6, the time is doubled. So instead of 3.62, it will be 3.62 times 2. Okay? So basically, the capacitor will take a longer time to discharge. So the capacitor question could look like this one. All right, moving on to the next one. So the next one is a little bit more spicier because they decide to put the capacitor like this side by side. Oh, instead of one capacitor discharging, now we have 2 because 1 is a lonely number. Okay, so define the capacitance of a parallel plate. Remember, we're going to use C is equal to Q over V, right? So this one is defined as the ratio of charge on one plate, the capacitor, to the potential difference across the plates. If you have the idea of ratio of charge to potential difference is 1 mark. And then you say, well, this charge is on one plate and the potential difference is across the plate. The context is the other mark. Okay, always provide context, especially in A2 definition. Don't just say charge over potential difference. Which charge? Potential difference across who? Right, part B, we have 2 capacitors in parallel to a power supply, and you're asked to show the combined capacitance. Okay, I'll show it here very quickly. This one is connected in parallel, so I expect the potential difference here to be E, and the potential difference to here to also be E, because they are parallel connection, so the potential difference will always be the same. Next. A certain amount of charge, okay, will be mobilized out from the negative terminal. Let's say this is Q total. Okay, we'll use thinner pen. Okay, so the charge will flow. You reach here. Junction decisions. Some of the charge will go here, Q1, and some of the charges will choose to go down here, Q2. So Q1, the electron on the negative charge here will be stored Q1. And then the negative charge here will be stored Q2. But don't forget, if one side is negative, the other side will be positive Q1. The other side will be positive Q2. The electrons will continue to flow. Okay. It's a bit like as I put more and more charge on one plate, the other plate is forced to give up its negative charge. But they don't talk to each other. It's not like the negative charge on one plate jump. They don't jump. So as more electron is put here, then more charges will move here. Okay. But regardless, the electrons are still flowing due to the push from the power supply. So from here, I can write an equation. The total charge is actually equal to Q1 plus Q2. Okay, and I know Q is equal to CV. So the total capacitance CT, and I guess the total voltage is E, is C1E plus C2E. I cancel all the E, right? CT is C1 plus C2. I should, okay, like that. It's a bit like deriving the total resistance equation. All right. So this one is 1 mark. This one is 1 mark. You also should probably add an explanation because C1 and C2 have the same potential difference as the supply E. That's why we can cancel the E. Yoink, yoink, yoink. This is the other mark. Parallel connection. Same potential difference as the supply. Okay. Moving on. I guess that's the easy one. Here is where it gets a bit weird, but it's pretty similar to the previous one, if you think about it. Do I still? Yes, I have. Very good. Okay. Let's compare them. This one, Feb, March, May, June, same year. Okay, the difference here is, for this case, if I put at X, it's connected to the power supply. See? Connected to the power supply. If it's connected to the power supply, this means the capacitor are being charged. There, connected to the power supply, capacitor is being charged. Okay, so we just need to check, is the capacitor connected directly to the power supply? Next, obviously, if I connect the switch at position Y, this is the closed loop. If there's a closed loop that does not involve a power supply, well, congratulations, ladies and gentlemen, we are now discharging the capacitor. Okay, yay. So they can draw slightly differently. In my brain, they look quite similar to me. But they're not identical. Okay. In this case, the resistor, there's an extra resistor here, the 25 kilo ohm. All right, anyway, here you're asked to show the combined capacitance of the two capacitor is 15 microfarad. So hopefully you already see the parallel one. So now you're going to see the series one. So 1 over total capacitance is 1 over 22 plus 1 over 47. So total capacitance is 15 microfarad. Because 22 and 47 is 50. But just in case you need it, just to confirm in your brain that you are doing the right thing, feel free to press in your calculator. This one is 14.99, so close enough. The working that we're looking for is this. Okay. The two-way switch is initially at position X so that the capacitors are fully charged. So again, the question will always try to be helpful to you. Using the information in C1, calculate the total energy stored in the two capacitors. Okay, automatic. Right now, I have a power supply of 12 volt. Okay, so this 12 volt is from here to here. By extension, this means that this is 0 volt. And you can see there's nothing here, right? So this is 12 volt. Think about your circuits, which means the potential difference across this whole thing is 12 volt. So if I want to find the energy stored, of course, I can find it in the individual capacitor. But since I already know the combined capacitance, the circuit can actually be simplified. I have a 12-volt supply, okay, and then I combine or I connect this to a 15 microfarad capacitor. So I can use E as half CV squared. Half 15 times 10 to the power negative 6 micro, 12 squared. This 0.5 negative 6. This would be 1.08 times 10 to the power negative 3. If you want to write 2SF, that's also okay. Okay, nice and easy. That's why we combine them. All right, so you can use the combination. Of course, you can also find it separately, but I don't know what's the potential difference individually. You may be asking, teacher, can we find the potential difference individually? Can. You can use ratio because they are sharing 12 volts. So if you want to, I can. I guess for the purposes of practice, I will show you how to find them separately. Okay, so this 12 volt is shared across these two. Just going to label it V1 and V2. Let's say, for example, decide to choose the long way. Not wrong, just long. V1 plus V2 is 12. Okay. Second thing, because they are in series, so whatever charge stored here, Q1 and Q2, will be the same as the total charge. So to find Q1, I will take C1 V1. To find Q2, I will take C2 V2. C1 is 22. I don't know what is V1. C2 is 47. Microfarad left and right can cancel. Okay, but what I can do is I can substitute. So from here, V1 is 47 over 22 V2. Okay, and I'm going to substitute. And I will sub into V1 plus V2 is 12. So 47 over 22 V2 plus V2 is 12 volt. So I can find V2. V2 would be 12 divided by 47 over 22 plus 1. This makes V2 88 over 23. Do I want to write decimal points? Can, but I will write more SF. So this will be 826 volt. If I find V2, I can immediately find V1 because V1 plus V2 is 12, right? So hence, since V1 plus V2 is 12, V1 will be equal to 12 minus 3.826. This will make it 8.174. Hence, we can now find total energy. You got two capacitors, so half C1 V1 square plus half C2 V2 square. Half C1 is 22 times 10 to the power negative 6. V1 is 3.826 square plus half C2 is 47 times 10 to the power negative 6, 8.174 square. Is it wrong? Nope, it's just long. So the beautiful thing about circuits, if you would call it beautiful, is that you can always check your working or your understanding, not during the exam. During the exam is not the time, but when you try your exercises. So you get a good sense of like, hey, I'm kind of on the right track, I hope. 817, 47. Of course, we will expect a little bit of variance because we are rounding some numbers. So I have 1.7 times 10 to the power of negative 3 joule. Well, it's not exact because this 15 is already rounded, but it's close enough. Okay, so you can do it this way, but I generally don't recommend because A, is too much work for too little marks during the exam. B, they already tell you to use this stuff, so it would be the same. Okay, so if you round it, this one is 1.1. There will be a slight discrepancy because this 15 is a rounded value. Okay, and also there's another slight discrepancy here because this obviously this 3.826 and 8.174 are not exact values. Okay, unless I press wrongly my calculator. Let me try. 2673. Yeah, if I use this ratio to find V1, this is 8.1737. Okay lah, it's the other extra numbers that affected the reading. Okay. But in other words, right, if you want to find, the important thing is to remember the properties. The sum of the potential difference across each capacitor in series is the same as the supply, and in series, the charge is the same. So it's different to the parallel, because the parallel one, the potential difference is the same, but the charge is a sum from the supply. Okay, so moving on. We're now going to push the two-way switch to position Y. And you're asked to find the time taken for the potential difference across the 22 microfarad capacitor to become 6 volt. Now, before you become very happy, by happy, I mean you just go and copy the equation. V is V naught E negative D over RC. You gotta calm down first. If you decided to put 6 here, which is fine, okay, I gotta know what is the V naught, what is the initial voltage across the 22 microfarad capacitor. Teacher, then you calculate already in this very long-winded working. Yeah lah, I calculated already lah. V1 is 8.174, but then, oh, I substituted wrongly, you guys. V1. Wonder. Okay, hang on, let me fix this working first. So I already find V1. This is V1. 8.174. This one is V2. 3.826. Maybe we'll get a closer number. But my point here is we already calculated, but we need to use this long method to find. So that's one option. I guess either way also, for this question, cannot run to fix the working. Hey, 1078. 1.08. Same. Beautiful. Okay. So in other words, right, you can count. Basically, you need to reach this point so that you know that this is 8.174 V1. So you need to show that working here. Or you might be thinking, how do I, is there a shortcut? Well, there is a shortcut, but we are going to borrow Q is equal to CV. Okay, it's not really a shortcut, it's just a shorter version of the working I did just now, less complete. That feels a bit weird. Okay, so the thing is, they are both in series, right? The capacitors are in series. So they will have the same Q. So if Q is constant, this means CV is constant. So C is inversely proportional to V. Oh, which means C1 over maybe C total will be V1, which is the V naught that you want, over V total. Do you know why C1 22 microfarad? Do you know the C total? Well, we just calculate now. It was 15. Do you know the initial voltage? I mean, this is the initial voltage that you want to find, V1. But you do know the total voltage across both, which is 12. So I think you remember some version of me telling you ratio will always be your best friend. If you know how to use it, then you don't have to go through the pain that I did just now. 15. So this would be, did I cross multiply wrongly? 12, 22 is V1. Oh, it's inversely proportional. It's time for food, man. See. Inversely proportional. So whatever that's below will go up. I bet whatever that's up will be. Which means this is 12. Total is 12. We're looking for V1. Okay, so that makes V1 12 times 15 over 22. You know it's wrong when it's more than 12. 8.181818. Okay lah, 8.18 is close enough to 8.174. 8.2. Stick to 2SF because all the data is 2SF. Then you can find the time because we know the resistance that they're discharging, 2.7 mega ohm. So 2.7 times 10 to the power of 6. Okay. And then the second thing that you need to think about is this value of C. Do I take 22? What do you think? Do I take 22? Kind of makes sense to take 22, right? Because we are looking at the discharging of the 22 microfarad capacitor. Feels like it makes sense to take 22. But the answer would be no, you cannot take 22. Why, you may ask? Well, this is because during the discharge process, both capacitors are involved. Because they are in series. So you can look at it like right now, when they want to discharge, whatever charge that is here will need to go through this capacitor before. So this electron will end up here, forcing this electron to continue to move. Like a relay race, you know, you pass the baton, you pass the charge. So the one that is moving or mobilized is this electron. So the discharge of the 22 will involve the 47, meaning this one's got to be 15, both of them. So 15 times 10 power negative 6. Well, the negative 6 and the 6 can go away. So I guess 6 over 8.2, if I want to, I can bring the ln over also, is equal to T over 2.7, 15. Negative. Yeah. 6 over 8.2. So it's 12.65 or 12.7 seconds. You want to write 2SF, you'll make it 13 seconds. So the capacitor discharge equation can look a bit sneaky because you've never seen it before. And sometimes they'll ask you strange questions where they combine the connection of capacitor in series and parallel, and then they'll put it together in a question like this. Okay. So what have we learned? The important things to learn from the question is if you are given a combination of capacitor, compared to the previous question, the question immediately becomes more complicated. But we have identities to use. For example, we can combine the capacitance and treat them as one single 15 microfarad capacitor to find the total energy. Okay. Number two, if they are in series, they have the same charge. So Q is constant. C becomes inversely proportional to V. You can use ratio to find the voltage. Okay. Of course, the next question will be, the teacher, what if they put in parallel? Well, as shown just now in the derivation, in parallel, you have the same potential difference or the same EMF. That means Q is proportional to V. And then if needed, you will do whatever that needs to be done. Yeah. So that you can find the Q naught that you need. If let's say you have two capacitors in parallel, like so. And then they discharge through a resistor R. So the difference between this versus the one that we have here, one capacitor, two capacitor, resistor R. Okay. So you will do this because they have the same potential difference. Q is proportional to V. Okay. And then the second thing is if you want to do the discharge equation, just make sure that you take one of the capacitor, and then at the end of the day, this C will involve both capacitors. So go and take the total capacitance. And at the end of the day, it's 3 marks. Okay. So if you write the equation and you substitute some values, even if it's not everything is correct, you probably can get 1. So unless you're aiming for very high and very good scores, pick and choose your battles. If your brain hang already, then 3 marks are, these other parts can get marks, right? Okay. So I think I want to do one last question, okay, which is actually I'll do the last 2 questions, which is the one from winter 2022. Okay. And I think I want to start off first with the one that I've mentioned before. I think maybe the May June 221 just killed everybody. So they make the question a bit easier. Look, Cambridge is still adjusting, okay? When the syllabus is new, they don't know how difficult they want to set the question. So they are just going to try a few different types of question, and you become the fortunate or unfortunate guinea pig. And then based on how the students answer the question, they will adjust the question. Okay. So what you can do as a student in this cycle, and what I've done when I was a student, is to just study the theory lah. Science is good. The theory will never change. Capacitor will always discharge the same way. So even if they ask the question in a little bit strange way, and you may not be able to score perfect marks, you'll probably be able to score 80 to 90% because your ideas are solid. Okay. So here, capacitance, resistor. Okay, this one looks normal now. And then you have two graphs. You have the Q against T and the V against T. They both go down exponentially. Explain the shape of the line in 6.3, representing the variation of V with T. Basically, why is this shape, the VT shape, the same as the QT shape? Well, we've explained it just now in our notes. I'm just going to roughly mention. I will say the current in the resistor is proportional to the potential difference across the resistor. So this is VR. Okay, this one. But we're going to link current and charge. So current proportional to voltage, Ohm's law. But also current is dq dt. So Since current is also the rate of charge flow, um, during the discharge process or when the capacitor loses charge. Due to current flow, the IT graph and QT graph are similar. Okay. So because of this, charge on capacitor is proportional to the potential difference VT decreases. Or the VT graph shows a decreasing trend. So say the rate of change of the potential difference decreases as the potential difference decreases. Okay, so in short, right, what we're trying to say is current is proportional to the potential difference, but also current is equal to dq dt. So if dq dt decreases, you can tell from the graph, this means current decreases, this means V decreases, this means dV dt also decrease. It feels like a very mathematic explanation, but what to do? You are describing the shape of the line. Okay. There are other points that you can write, but they are related to the question, but doesn't really lend itself to the explanation. Okay. So write whatever that you think is relevant. Normally, if they ask you to explain something that is very like out the, I want to say from the left field, meaning we don't expect, then you just write whatever that makes sense. Okay. All right. Moving on. So for this one, show that the time constant in the circuit is 5.5 seconds. You don't have value of RC, but what you can do is you can write the equation. Let's say I start with Q. Q is Q naught E negative T over RC. So when the time is equal to RC, Q is equal to Q naught E negative. The time I substitute with RC. So we've did this before in our notes, but this is E negative 1 or 0.37 Q naught. Do we have Q naught? We do. Look at the graph. Q naught looks like 0.9. So I am going to substitute 0.9 here. So Q is equal to 0.37 times 0.9. This will make this 0.333 millicoulomb. So now I go back to the graph. I probably need to show the graph, right? So figure 6.2, 0.3. So 0.3, 1, 2, 3. 3 is like half a box. So paper 4, you can read half a box, okay? So half a box here looks like 5. I mean, 0.33. Wait, 33 is here. Ish. So it looks like 5.5. Roughly lah, just show on the graph. Okay. So this is one method. Read directly from the graph. The time is 5.5 seconds. So from graph, when Q is 0.33 millicoulomb, The time is 5.5 seconds. Hence, time constant is 5.5 seconds. Or use the equation, choose a point on the graph, but you choose a point that looks nice lah, okay? So you cannot choose the 0 point because you need this 0.9. This is my Q naught. But I guess you can choose, again, maybe I choose this one lah. When T is equal to 15, this Q looks like one box, which is 0.05. Okay, we are going to substitute all of that inside. 0.05 millicoulomb is 0.9 millicoulomb. So the millicoulomb cancels off. E negative 15 over RC. We're looking for RC. So I'm going to have ln 0.05 divided by 0.9. Because bring over, divide, and transfer the ln over. This would be negative 15 over RC. So from here, RC is equal to okay, close enough. 5.2. So never going to be identical. The graph is not very accurate. So hence, time constant is 5.2 seconds. I think there are other values that are slightly more accurate that can lead you to 5.5. But yeah. Okay. So I prefer this one. This is generally more accurate because you only take one reading. This one you take two reading. You take 0.05, take 15. Okay. So yeah, up to you lah. Both are fine. Just show you're working clearly. And if you do this way, because you take a coordinate, this one is generally for paper 4. If you're not using an identity like my first method, so if you are choosing a coordinate, like for example, I read that one box, it may not be accurate one. So you need to repeat times 2 and then average. Meaning you repeat again, choose another coordinate. It's a lot of work lah. Now I remember why I don't recommend. So you choose another coordinate here and here. Throw inside and do again. And then find the average. Okay? So don't recommend. Prefer to do this. If you want to see how it looks like, you can always refer to the mark scheme. But this is nicer. This one. This is better. Highly recommend. Because we have one. And then you can just read a point. Here you need to read 2 points. Pain. Okay, next. Using all the information that we have, find C and R. Well, this one now becomes very easy because you can think about your Q as equal to CV. So 0.9 millicoulomb is equal to C. And the potential difference, the initial potential difference here, V naught is equal to 7.5. So the potential difference here is 7.5. So this means your C would be 0.9, 112, 120 microfarad. Finally, you want to find resistance R. Time constant is equal to RC. We have time constant, 5.5, looking for R. This is 120 times 10 to the power negative 6. So from here, your R is 4.58 kilo ohm. So 45 kilo ohm, 46 kilo ohm. Okay. So the part that is a little bit blindsided is mainly the explanation here. All right. Because these two things are parallel. So the potential difference across both of them will drop at the same time. Okay. So after you explain, when you want to find the time constant, this is recommended. Okay, so it's not as simple as just using the equation. They will test your familiarity of the equation in few ways. It's not just you see their values, you can substitute. You must really know how the graph looks like, how to use the graph, and how to use the information from the question and the circuit drawing to deduce the equation. Okay, so the more you know about the equation, the easier the question will eventually be at the later parts of the question. Okay, so that's it for capacitors. I think I want to leave. This one actually has some magnetic induction. So I'm going to leave this until we have time to talk about magnetic field, which will be next week. So we keep this for magnetic field. I'll probably remember to revisit this. So what we have not done, if you refer to the key questions, are the questions that have so go try this. This one is already recorded, but you really need to think about it and make sure you understand the charging and discharging mechanism on page 17. Okay, again, it's always part of it already. I've selected some older series parallel capacitor question. You should try them and ask me if you have problems, but generally people find this doable. Okay lah, that's all. Just make sure you do some circuit. Basically do the questions that I've collected. If you can do, you understand them, you're okay already. All right. So what remains is magnetic field. Maybe this one needs a bit of help. So let me know if you need me to discuss this question from page 25. But the rest should be doable. So try out the key questions in your own time. Okay. You can just use this as a reference and then open to wherever you do your question set or wherever you have printed out. All right. Have a good week ahead. Thank you for voting if you did vote for yesterday during the state election. I'll see you next week. That's all. Take care. Have a good week ahead, guys.